Alright, this is going to be a video on waves and sound. And a wave is any kind of a disturbance that moves from one place to another one, and energy is transferred when a wave moves. We have a transverse wave, and in that case the particles are moving up and down while the wave is going this way. So since the particles go up and down and the wave is going this way, that's perpendicular. And whenever the wave motion is perpendicular to the direction of the wave, then it's called a transverse wave. A longitudinal wave, the particles move in the same direction as the wave. In other words, here the particles are vibrating back and forth this way, and the wave is also moving this way. So in that case, it's moving in the same direction. So that's a longitudinal wave. Sound waves are longitudinal. That's why they have a picture here of a speaker. Water waves are transverse waves. Here they're showing us water waves that are transverse. We can also see that in addition to transverse, there are some longitudinal waves. So water waves can act as both. Specifically, if we want to think about examples, light and all electromagnetic radiation travels as a transverse. And I stated earlier that sound is a longitudinal. Okay, when we look at a wave, the wavelength is the distance between two corresponding points on a wave. So if we're thinking about a transverse wave like this, the wavelength could be from a crest to a crest. That would be one wavelength. Or if we think about a compressional wave, there's where it's compressed, and farther apart, and then compressed together, and then farther apart. Or sometimes you're going to see them like coils, like the coils are tighter together, and here the coils are spread apart and then tighter together. If we would go from the middle here to the middle here, two corresponding points, that would also be a wavelength. And for wavelength, they use the Greek letter lambda, so that's going to represent wavelength. The period is the time it takes for one wave to pass a given point. And period is time, so that's why it's given with a capital T. And frequency tells us the number of waves per second or per given time. So number of waves per time. And frequency is the reciprocal of period, which means if I take 1 divided by the period, I get my frequency, or vice versa. Period is usually measured in seconds, and frequency is measured in units called hertz, Hz. And if we wanted to know the speed of a wave, we know that the velocity is equal to wavelength times frequency. And your wavelength is going to have to be in meters, and your frequency would be in hertz, and you would end up with meters per second for velocity. And this equation, the one that I have boxed, you're going to be using in problems 14.2 on your assignment. You'll also be using it on 14.4 and on 14.28. Okay, the speed is determined by the medium. That's extremely important. So the speed does not change unless the medium changes. And what we mean by the medium is what it's going through. And so if we're talking about a string, we would be looking at the tension. So as long as the tension stays the same, or the mass of the string stays the same, the speed would stay the same. However, if you change the tension in the string, like increasing the tension, that's going to make a wave go faster. Or if you increase the mass of the string, then it's going to be harder for the wave to go through and going to be slower. But as long as your medium stays the same, in other words, what it's going through, as long as that string or the spring or the water stays the same, the speed is the same. The frequency and the wavelength will vary inversely, meaning as one goes up, the other goes down. For example, this has a high frequency compared to this. And we can see that the higher the frequency, the closer the waves are together. So small wavelength, high frequency. Here we have a large wavelength, but we have a small frequency. So those vary inversely. So if you change frequency, you change wavelength or vice versa. But the speed is going to stay the same as long as your medium stays the same. And since frequency is related to period, that means if you change the period, the wavelength will change, or vice versa. And since period is the reciprocal of frequency, that means period and wavelength do the same thing, but frequency and wavelength do the opposite thing. And that is going to be used, that information, on the problem that's about strings. And there's also one on conceptual exercise, so I'm going to put CE, conceptual exercise 14.2 on your assignment. Deals with that relationship. All right, if we want to know the speed of a wave on a string, we can be looking at force. Larger force equals a faster speed, and you can be looking at the mass per unit length. In other words, if we look at how dense that material is, and the larger the mass, the slower the speed, as we said before. This is an alternative one using force and mass per unit length, but the ones that I showed you on your assignment, the 14.2, they're going to use that other equation that we use, so you probably will not see this too much on your assignment. Okay, if we look at waves, they can reflect off of boundaries. In this case, this is a fixed end, which means the wave hits here and it's going to be reflected back. And if it's fixed, it can't move. So if the wave goes in on the top, the crest is on the top, that means when it comes back, it's going to be a trough. It's inverted, meaning it comes back on the opposite side. A free end is going to where it's been able to move up and down here, so we can see that this ring would slide up and down. In this case, it is not inverted. It's still reflected, meaning it still bounces back, but it's not going to be on the opposite side, which means if it comes in on the top, it will come back out at the top. So for fixed end, they invert, but for a free end, they do not invert, even though they're both reflected. And one other thing that I probably should mention that I kind of forgot to mention was amplitude of a wave. The amplitude is how much energy we put into it. So if you're thinking about a slinky, it would be how hard you would flick it. So it's the amount of energy that you put into it. Or if it's sound wave, it's how loud it is. And the amplitude would be how high that wave is. And how high that wave is has nothing to do with the frequency. So the amplitude is not related to the frequency at all. It's independent. The amplitude is only related to the amount of energy that we put into the wave. And a bigger wave, a taller wave, would be more energy and therefore a higher amplitude. The amplitude, if you remember from last chapter, it is from the equilibrium spot to either the bottom or the equilibrium to the top. All right, we said earlier in the first slide that sound waves are longitudinal, and there's two different regions. In a transverse wave, we talked about crests and troughs. So in a transverse wave, here we had our crests, and down here this is a trough. In a longitudinal wave, we have regions called compressions. So this would be an area of compression where it's compressed together. And then we have areas where they're spread apart, and that is like right here, and that is a rarefaction. So this is a compression, and then we have the stretched region, and this stretched region is called a rarefaction. And if we wanted to find the wavelength, it's got to be between two identical parts of a wave. So, for example, beginning of a rarefaction to the beginning of a rarefaction would be a wavelength. Or middle of a compression to the middle of the next compression would be a wavelength. So, compressions and rarefactions. All right, in a sound wave, we look at the amount of density. So here would be a compression where the particles are really squished together. And then here where they're spread farther apart, there's less pressure. That would be a rarefaction. So here we can see wherever there's this dense region, that means there's high density. And here in these lower regions, this is less density, or in other words, higher pressure and lower pressure. So this would be like your compression, this would be like your rarefaction. Okay, we said the speed depends upon the material. The denser the wave, the faster it goes if we're talking about longitudinal waves. So the speed of sound is going to be the fastest when we have a densest material, because in a longitudinal wave, those particles have to vibrate back and forth. And the closer they are together, meaning the more dense they are, the faster that energy is going to be able to travel between the particles because they're closer together. So when we look at things like aluminum and granite that are very dense, their speeds are high. Things like air down here, those are fairly low. And we can see there's a difference in temperature. It's traveling faster at higher temperatures, and that's because more temperature means faster particles, so the particles move faster, therefore the energy is going to travel faster. So temperature does make a difference in there as well. When we talk about sound waves, we have the audible spectrum. This is the part that we can hear. This is somewhere in the neighborhood of 20 hertz to 20,000 hertz for the frequency. Ultrasonic means frequencies are greater than 20,000 hertz. So these would be things like dog whistles that we can't hear. And those have medical applications, obviously ultrasounds. There's also infrasonic ranges, and those are frequencies that are less than 20 hertz. And those would be things like elephants and whales. We are not able to hear those frequencies. Those frequencies would be lower than what we could hear. Okay, and we look at sound intensity. Intensity has to do with the loudness of the sound. And the sound intensity will decrease as the square of the distance. It's another one of those inverse square relationships. So here's our intensity. And here is the distance, this radius that you are from the source. And they talk about radius because if this is like your speaker, that sound travels three-dimensionally. It spreads way out. So it's kind of like a radius when they measure it, since it's conical. P stands for your pressure. And pressure is going to be in watts. And then 4 is a number, pi is pi. R is the distance, and it's going to be squared, and that distance has to be in meters, and then you square it, so it's meters squared. So the intensity is given in units of watts per meter squared. And that intensity equation you're going to be using in your assignment on, there's a problem called, I think, car stereo. That's going to be using that relationship. And also 14.34, that exercise, uses this equation, power and radius. Intensity, again, watts per meter squared. It's possible they might ask you to find the pressure, or they might be asking you to find the radius. So just be aware. Oh, and sometimes pressure, they also talk about power, since it's in watts. They might ask you to find the pressure, the power. They might ask you to find how far away you are, but those are going to be the variables that you're going to find in that equation. Sound intensity, bats use this also, and they can be able to locate objects in the dark by taking a look at the decrease in the sound intensity. When we talk about sound intensity, the way that humans measure sound is in decibels. And a decibel, the relationship is 10 times the log of I over I0. And I0 is called the threshold of hearing. That's the faintest sound that you can hear. and this number is I0, so that always goes in for I0. I would be the intensity now compared to the threshold of hearing, the lowest sound that we can hear, the faintest sound. Then we do the log of that ratio and take it times 10, and that's going to tell us our decibel reading. And usually when we talk about intensities of sound, instead of measuring it in watts per meter squared, we talk about relative intensities, meaning compared to the faintest sound that we can hear, and those are in decibels. Okay, so B is a bell, dB is decibel, tenth of a bell, and we can see the intensity doubles with each increase in 10 decibels. So here is some decibel ratings. 160 is where an eardrum ruptures. A loud rock band, like after a concert, a lot of times your ears will be ringing, and that's because we have very high intensities. Things that are fairly quiet, whispers, are 20. This threshold of hearing is 0, which corresponds to the 1 times 10 to the minus 12 watts per meter squared. Rustling leaves is 10. And we can see here this increase in 10 decibels means that it's 2 times the loudness. So in other words, it doubles for every 10 increase in decibels. Which means if you increased from 50 to 60, this would be 2 times, and from 60 to 70 would be another 2 times. So from 50 to 70, that would be 4 times as loud. Okay, the Doppler effect is the apparent change in the pitch that we hear. The pitch of the object doesn't really change, but what happens is if we move or the source moves, then the pitch sounds different. And by pitch, we mean the highness or the lowness of that sound. And if we are moving toward the source, or the source is moving toward us, the speed or the frequency appears to be higher. If it's moving away from us, then the frequency appears to be lower. And if we have a moving observer, meaning like the person is moving, but the sound is the sound wave, the source is staying the same, this would be the equation that we're using. F prime stands for the new frequency, the one that we would be hearing that's higher or lower, depending on if you're coming away or towards. F is the frequency of the source. In other words, if it's a whistle, what is that frequency normal? Is it like 256 hertz or 128? V is the wave speed, and this mu, this is the source speed. So this would be the speed that you would plug in there for whatever the source is. We can see mu divided by V, and then there's brackets around here, and you take it times the original frequency. And the SI unit that we're going to use for frequency is seconds to the minus 1. That's the same thing as hertz. There are 2 equations that we're going to be using for the Doppler effect, one for a moving observer, and there's one for a moving source. So this is the one for the moving source. And you will be using those equations there in the assignment. One of them is called the Doppler effect problem. The other is 14.46, and again in 14.90. Those 3, I'll use the Doppler effect, and you might be moving the source or you might be moving the observer. Depending on which scenario you have, you'll want to use the appropriate equation. This slide says the Doppler effect from a moving source can be analyzed similarly. Now it's the wavelength that appears to change. In other words, here is the stationary observer, here is the source, and notice this source is putting out waves. So let's say this is my siren. It's putting out sound waves. As that moves, so let's say it's right here now, it's going to emit new sound waves. So it looks to me as if those wavelengths get smaller. And because the wavelengths get smaller, then the frequency appears to be higher as it's coming toward us. So the wavelengths don't actually change, and the frequency doesn't really change, but it appears to change because those wave fronts get compressed together. Okay, and here, this is, the source is moving, so that's your mu. We can see like this truck would be moving and it's got its horn blaring. The wave speed would be the speed of the wave through the medium. Like, for example, how fast sound travels through air. or water or whatever it is you're going through. Okay, when the source moves faster than the speed of sound, we can hear a sonic boom. And this is a graph that's showing the perceived frequency and the speed. And there is a video that I'll probably show you in class about sonic booms. This equation you can move if you have both a moving source and a moving observer. So in that case, you can see it's both equations together. One time we had it on the top, one time it was the bottom. So this is both the observer and the source moving. Okay, this is showing us Doppler radar that they would use in the news. And here they're showing you a hook echo, like from a tornado. And here we have an ultrasound, or they're going to use the Doppler effect here, using a Doppler blood flow meter. And then there's a video here that you can listen to the Doppler effect. And then there's another video there using the Big Bang Theory. Pretty entertaining. Superposition and interference. Waves travel through mediums, and when they get together, they add together. So if I have one wave that's traveling here, and I have another wave here, then they can share that same wave. So in other words, one person sends it from this end, one sends it from this way. And when those two get together, they would combine their amplitudes, which means when they get here in the middle, I would have this wave plus this wave, so I would end up with an even larger wave that would be formed. So if I go back here to a picture, we could have an even larger wave that was formed. And then there is another video for you to watch on interference. In this case, they're going to show us constructive and destructive interference. So here's our two waves, one from each direction. They're coming closer together. When they get in the very middle, we can see they add up to an even larger wave. So that's going to be constructive interference. And then after they combine, they just simply go off in the other direction. So this one keeps going this way. There it is. And this one keeps going that way. So here it is. So they don't bounce off one another. They simply pass through one another and keep on going the same direction. And this one, this is going to be destructive, because when these ones meet, they're going to cancel out, because I had a crest meeting with a trough. So in that case, well, they're going to meet and they're going to cancel out. And then they simply pass right through each other and go on their way as before. This also occurs in two-dimensional waves. Here we can see we have one wave and another wave, then they get together. Here's our two sources. And we can have spaces where we have constructive and destructive. So constructive is where we have two crests meeting up together, and destructive is where they're going to have regions that are going to cancel out. So you can create what's called an interference pattern. If we have two sources meet, obviously we're going to have constructive interference wherever two crests meet, and in between there's going to be destructive, where you have a crest meeting with a trough. Okay, and the last section that we're going to look at is on standing waves. And a standing wave is one that looks like it's not moving. So it stays in one place. And it just oscillates either from a crest to a trough or back and forth. So this could be like a jump rope where it's just going up and down and up and down and up and down. That'd be a standing wave. It doesn't look like the wave is generated and goes through and then comes back. It's just up and down or up and down. And this, a lot of times, we're going to look at musical instruments when we look at standing waves. And we can see that they're looking at two identical points on the wave. So from the beginning here to the beginning here, that's going to be one complete wavelength. Notice this one hump is going to be half a wavelength. So this would be half of a wavelength. The lowest frequency that we can have is what's called the fundamental frequency. And if we have higher frequencies than that are multiples, those are called harmonics. Now, if we're looking at a string, we can have the fundamental frequency, and the fundamental frequency, the frequency is going to be equal to the speed divided by 2L. Or my wavelength is going to be 2L. So if this is my fundamental, we have a crest and then we have a trough, and it's either going up or down. Since this is 1/2 of a wavelength that fits on this one length of rope, that means the wavelength would actually be 2 times that length, because I'd have to have a whole nother length here in order to have one crest and one trough together. Now, if we have a harmonic of this, so this is our fundamental, this would be the second harmonic, where I have 2 antinodes. And the second harmonic is going to be 2L divided by the harmonic. So the wavelength of this one is going to be 2 times the length of the rope divided by the second harmonic. And the third harmonic would have 3 antinodes, 1, 2, 3, and this wavelength would be 2L divided by 3. And the frequency of this one, if this is F for the fundamental frequency, this frequency would be 2 times the fundamental, and this frequency of the third harmonic would be 3 times the fundamental. So let's say that I had the fifth harmonic. I don't know, 1, 2, 3, 4, 5. Not very pretty, but that's the fifth harmonic. My wavelength would be 2L divided by the harmonic, so 5, and the frequency of the fifth harmonic would be 5 times the fundamental frequency. So if your fundamental was, let's say, 50 hertz, then the frequency of your fifth harmonic would be 5 times 50, which would be 250 hertz. And we can see the frequency here is a lot bigger than what it was here, because those waves are squished up closer together. And the wavelength then would be smaller. Nodes are places that don't move. Here, 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 or here, 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 or obviously here at the two ends. The antinodes are the points that move. So that's the humps that you have. So 1, 2 antinodes, or 1, 2, 3, 4. This is the third harmonic, and notice it has 3 antinodes. So the number of antinodes tells you the harmonic. And then the number of nodes, this is the third harmonic, and it has 1, 2, 3, 4. The number of nodes that we have is the harmonic plus 1. In other words, this is the second harmonic, and it has a total of 3 nodes, counting the ones on the end. If we have strings with different densities, that means they're going to have different lengths and different densities. They're going to have different fundamental frequencies. And in a guitar, the strings are all the same length, but the density varies, meaning the thickness of it varies. Okay, in a piano, the strings vary both in length and in density, and this gives a large amount of frequencies possible. If the length and the material of the string is decided, the strings may be tuned to the exact frequency by changing the tension. And that's like on a guitar where they have that little screw that you can move. And musical instruments are designed so that the variation in tension between the different strings is small. This helps prevent warping and other damage. And when we're looking at fundamental frequencies and harmonics, let's see if there's space to write over here. We're looking at standing waves. This is going to be 14.70 deals with this, 14.72, and 14.92. All those are dealing with the harmonics. And those equations that we had, like 2L divided by the harmonic, and that the frequency was the harmonic times the fundamental. And we still can be using this one. So in other words, when you find the wavelength of the fifth harmonic by taking 2L divided by 5, and you know the frequency, you can find the velocity, or vice versa, depending on what it is you want to find. Standing waves occur in air. They occur in all kinds of musical instruments, not just stringed instruments. In this case, we have an antinode at one end and a node at the other end where it's closed. So a lot of times they talk about open pipes and closed pipes. So if you have one end open and one end closed, then the fundamental wavelength is 4 times the length of the rope. Instead of 2L, it's going to be 4L. 4L divided by whatever your harmonic is. So for strings, it was 2L divided by the harmonic. But if it has one end open and one end closed, then it's going to be 4L divided by the harmonic. And you only have odd numbered harmonics. Here in a string, you can have all the harmonics. You could have the fundamental, you can have the second, the third, the fourth, the fifth, the sixth, seventh, and so forth. If you have one end open and one end closed, then you can only have odd numbered harmonics, meaning you are not going to have a second harmonic or a fourth or a sixth. And it's 4L divided by the harmonic instead of 2L divided by the harmonic. So there's a major difference between having an end that's open and one end closed versus if both ends are closed. If both ends are closed or both ends are open, then it's just like a string. But if one is open and one is closed, then it's a 4L. Those would be like organ pipes. Okay, like I said before, if both ends are open, the frequencies are the same, just like in strings. So we use the 2L divided by the harmonic, and we can have all harmonics again. Okay, beats. This is between constructive and destructive interference. And when we were looking at all that constructive and destructive interference and that law of superposition, I didn't tell you a problem. Pulses on a coil spring, I think it is, pulses on a spring. That problem on your homework deals with this constructive and destructive interference that was back on those other slides, talking about when they add together you get constructive, and when they interfere you get destructive, when they cancel partly each other out. Okay, beats is when you have two different frequencies that are fairly close together and those interfere. So here we can see that this is one wave and this is our other wave. So when these two get together, notice I have this very large amplitude that adds together, and then here they partially cancel out. And then I have a big amplitude, and then it cancels out. And a beat kind of looks like this pattern. And in our lab that we are doing, you're going to get a region that kind of looks like this. And then it goes down, and then it gets bigger again. And then it goes down, and then it gets bigger again. And you frequently hear this, like when instruments are tuning, it's kind of this warbling sound, this wah 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 wah. That's going to be the beats that you hear. And your beat frequency, the beat frequency is the difference in the two frequencies. So frequency 1 minus frequency 2, and just the difference between them. So in your lab, if you were looking with two tuning forks, let's say one had 250 hertz and the other one was 256 hertz, the difference in those is 6 hertz. So this is your beat frequency. And if your beat frequency is 0, then that means the difference in the tuning forks is 0. So they are the same note, and you will not have beats that you hear. So when you hear fast beats, wah 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 wah, versus slow beats, wah 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 wah. And like I said, you hear that in band, like when you're tuning. Saxophones are notorious for this, and flutes when you're listening for those. And piano tuners in the old days used to bring tuning forks along, and they would play the tuning fork, and then they would listen to the note on the piano, and they were listening for these beats. And you're looking for a beat frequency of 0. That's going to mean that they're in tune. And on your assignment, 14.80, that one is dealing with this concept of beats and beat frequency. And there is one other one on your assignment. It's 14.26. And it kind of deals with that velocity is frequency times wavelength. But it would probably be easier for you to understand if you think about distance is rate times time. They're talking about sending a note and then having it come back and hearing the echo. Keep in mind, if you send it and it comes back, that distance is twice. So if that time takes to go there and back, you're going to have to double that distance. Because the echo, in order to hear the echo, the sound wave had to hit there, get to the bottom of the well, and then bounce back. And I think that's going to be all the ones on your assignment, and that gets us to the end of chapter 14.